In this presentation, I am going to explain previous GATE questions and answers for the year 2026. And the topic covered is analog electronics. Now let us see the first question, 2026 GATE question that carries 1 mark. The figure shows a straight line approximation for the forward characteristics of a power diode. That is this one. This diagram shows a continuous on-state current of 15 amperes is flowing through the diode. So through this diode, 15 amperes is continuously flowing. And what is the power loss in the diode? That's the question. The options are option A, 32.8 watts, option B, 21.2 watts, option C, 18.6 watts, and option D, 23.1 watts. Now, what is the power loss of this diode through which a continuous current of 15 amperes is flowing? And the approximation, it's a straight line approximation, is the voltage across the diode and the current through the diode. This is the straight line approximation of the forward characteristics of the power diode. Now coming to this one, corresponding to 15 amperes, you have to find out what is the voltage drop. Once you get the voltage drop corresponding to 15 amperes, that voltage drop into this current 15 amperes will give the power loss. Therefore, you have to find out what is the voltage corresponding to voltage drop corresponding to 15 amperes. Therefore, this is the plot for a 50 amperes and here it is equal to 1.8 volt. Now corresponding to 15 amperes, that is corresponding to 15 amperes through the diode, let us see what is the voltage drop across the diode, power diode. Now I am marking it as X. Now if you write the corresponding, the slope of this line, that is tan theta, that is, let X be the voltage across the diode corresponding to 15 amperes. Now the slope of this line, the slope of the line is given by tan theta. So tan theta can be written as this one, that is 50 divided by 1 point, here this tan is equal to 1.8 minus 1. Therefore it is equal to 1.8 minus 1, this base. That's same as, because this is equal to this one, that is this one is equal to 15 amperes. 15 amperes divided by this 1, or x minus 1. X minus 1. Therefore that is, we are writing the equation for the slope of this line, it is tan theta, which is given by this one. From this equation, if you calculate the value of the x, you will be getting it is equal to 1.24. Therefore here this is equal to 1.24 volt. Therefore when a 15 amperes is flowing through this power diode, the voltage drop across the diode is equal to this one, which is x, it is equal to 1.24 volt as such. Therefore the power loss is equal to, the power loss in the diode is equal to whatever the current flowing through the diode, that is 15 amperes, into the voltage drop across the diode, which is equal to 1.24. The 1.24 into 15, which is equal to 18.6 watts. Therefore the answer is the option C. Now let us see another question, 2026 GATE question that carries 1 mark. Consider the circuit shown, that is this one, a diode, an inductor and a resistor. Assume that the diode is ideal. This diode is ideal and the supply voltage is given by, it is equal to 325 sine 2 pi 50 into t, that is sine 2 pi f into t, or 50 is the frequency, that much voltage is the input voltage, and the inductance value is given by 500 microhenries and the resistance equal to 10 ohm, and the peak diode current in amperes is, that is to be round off to the 1 decimal place. Therefore what is the peak current through the diode? Therefore this is the circuit in which the voltage source is given by 325 sine 2 pi into 50 into t, and the inductance value is given and the resistance value is given. Therefore the circuit is like this one, and first we have to calculate what is the during the positive half cycle, of course the diode will be conducting, and what is the current, or for that we have to calculate what is the impedance as such. We have to calculate what is the impedance here. Resistance is there, the inductance is there. Impedance is Therefore, in order to calculate the inductive reactance XL is to be calculated. That is, it is equal to 2 pi into, it is equal to omega L, 2 pi into 50 into L. L is equal to 500 microhenry, 500 into 10 raised to minus 6. And that comes around 0.157 ohms. Therefore, the inductive reactance is given by XL equal to 0.157 ohms. But the resistance value equal to 10 ohm, because that means that resistance is very, very large compared to the inductance. Therefore, the impedance, if you calculate, it is equal to square root of R square plus XL square, or square root of 10 square plus 0.157 square, or that's equal to 10.001, that much ohms. That is almost nearly equal to the resistance value, because the inductive reactance is very, very less compared to the resistance. That is why impedance value is almost, magnitude is same as the resistance value. Therefore, that is why we are approximating that impedance as the resistance value 10 ohms. Then we can calculate what is the peak value of the current. Peak value of the current equal to peak value of the voltage is given by, which is equal to 325. That 325 divided by the impedance, of course that's the resistance value already calculated, that divided by 10, which is equal to 32.5 amperes. So the peak value of the current through the diode is given by 32.5 amperes. Now let us see another problem, that is 2026 gate question, that also carries 1 mark. Consider the circuit shown in the figure, that is figure this one. Figure, a gate pulse of Vg is applied between the, between time, because time instants, that is between this time instant of these two time instant, T0 and T1, the gate pulse is applied T0 and T1. After T1, that is after this point, after T1, during the MOSFET turn off period, the MOSFET is getting turned off after T1, then it experiences a voltage overshoot, that is overshoot voltage is experiencing, that is, and that is plotted here as such, that is based on the VDS value, that is drain to source value waveform shown in this one. This is the VDS value, this is the overshoot as such. Question is that which one of the option is correct? Which one of the option is correct? Option A, the magnitude of this resistance, that is this RF, we can say that feedback diode is the feedback resistance, is the inductor is the, this feedback resistance I can say that RF, which is equal to that, the magnitude of that one R1, this is corresponding to R1 is corresponding to this one, first one, and this is corresponding to R3, and this is corresponding to R2. Therefore, here telling that R1 is more than R2 more than R3. Second option B equal to, which is equal to this R1 is more than R3, which is more than R2. Option C, which is equal to R3 more than R2, which is more than R1. Option D, which is equal to here R2 more than R3, which is more than R1. For out of these options, which is the correct for that one? That when the MOSFET is getting turned off, the VDS is changing suddenly. It's after T1, suddenly like this one. For different values of the feedback resistance, after then which is correct? Out of this three, these four statement has been given, which is the correct out of this four value of this resistance. Now we can see that when the overshoot here, the path is like this one. When the switch is off, there will be a current through the diode resistance and through the inductor. An RL path is building up. Therefore, here as the current, the current path is like this one. Of course, the time constant is given by L by R. L by R of this circuit, the resistance and inductance is the L by R is the time constant of circuit. Now we have to, based on that one, we have to explain out of this one which is more, R1, R2, R3, like that we have to find out. Therefore, of course, as L by R is the time constant, as resistance increases, time constant is reducing. Therefore, here you can say that one, this here it is suddenly changing, or the time constant is least for this one, and the time constant is more maximum for this case. Therefore, as the time constant is increasing, the resistance value is reducing. Therefore, here let us see what one for that one. That is why based on that one we can conclude out of these three which statement is correct. Let us see another next slide at that one. Now continuing the same problem, 2026 gate question, and the MOSFET is turned off. As already explained, the MOSFET is turned off at this instant. And here when MOSFET is turned off here, the inductor current must continue flowing this loop from that forms RL, or that is since inductance transient with MOSFET capacitance, which produces an overshoot in the voltage, drain to source voltage. Here the resistance R1, or that resistance, that RF, okay, feedback resistance, that dissipates the stored energy. Therefore the time constant of the circuit RL, that is given by L by R, and as the resistance increases, the time, because it's the inverse relation, as the resistance increases, the time constant reduces. The time constant reduces and the overshoot increases. Therefore in that case, that is why here for the statement, this R1 value will become, that will be, time constant is least for that one. Therefore R1 value is the maximum, next value is equal to R3, and the next value is equal to R2. Therefore R1 is more than R2, more than R3, and which is more than R2. Therefore the solution is the option B. The answer is option B. Now let us see another problem that also carries 1 mark, 2026 gate question. In the linear regulator circuit shown, that is this one, Zener regulator, the base to emitter voltage VBE of the BJT bipolar junction transistor is equal to 0.6 volt. So for VBE is equal to 0.6 volt with the polarity plus here and minus here. And the Zener voltage clamps to a bias voltage of 5.4. Zener breakdown voltage equal to 5.4 with a polarity here, minus here, plus here. Ignore the biasing circuit of the Zener diode and the bipolar junction BJT. The maximum possible efficiency of the regulator is how much? That is, what is the efficiency of maximum possible in this regulator? That is the question. That is to be round off to 1 decimal place. Now this is a voltage regulator, Zener voltage regulator, in which the input voltage is given, that is equal to 10 volts, and here the VB is given, and the VZ or Zener breakdown voltage is given, and of course the load current is given as, of course, equal to 100 milliampere is the load current. And now here Zener, what is the the efficiency? Efficiency is nothing but output power divided by the input power. That is expressed in percentage into 100. That is output power P out divided by P in, that into 100. That is the efficiency of this regulator. Now coming to the first output power. Output power, let us see that one. Output power means we have to find out what is the output voltage. Output current is equal to already 100 milliamperes it is given. For output voltage is, if you write the the KVL, Kirchhoff's voltage load to this loop, here this is a potential rise, this is a potential drop, and this is also a potential drop. Therefore this one plus this equal to this, or here this is equal to the output voltage is given by, which is equal to 5.4 minus 0.6. 5.4 minus 0.6 is the output voltage. Therefore here it is given the Zener voltage VZ equal to 5.4, and if it is equal to VB equal to 0.6 volt, and the output load current is equal to 100 milliamperes, then we can calculate the output power, which is equal to the output voltage into the current. Output voltage is given by, as I already explained, it is equal to VZ minus VBE, or that is equal to 5 ampere, that is therefore that voltage, output voltage is given by 5.4 minus VBE 0.6, that much voltage into the load current 100 milliamperes, that comes 480 milliwatts. Therefore the output power is given by 480 milliwatts. Now let us see the input power, that will be explained in the next slide. Therefore this is the voltage regulator in which the load current equal to 100 milliampere, and the load voltage is equal to, here it is equal to 5.4 minus 0.6 volts. Then you have calculated what is the output power. Now let us see what is the power at the input side. Now continuation from the same problem. Here we have to calculate what is the efficiency. Output power already we calculated, which is equal to 480 milliwatt. Now we have to calculate what is the input power. Power at the input side. Power at the input side means input voltage into the input current. In order to calculate the input current, it is a summation of the collector current plus this current through this resistor. let us see what is the current through this resistance. Therefore, the current flowing through 5K resistor, that's equal to this voltage equal to 10 volts and this voltage is equal to 5.4 volts. Therefore, the difference in voltage equal to 10 minus 5.4 divided by this resistance, which is equal to 5K, it is equal to 0.92 milliampere. Therefore, this current equal to 0.92 milliampere and the collector current is, which is almost equal to the emitter current because the base current is very less. That is why the collector current is almost same as the emitter current or the load current, which is equal to 100 milliamperes. So the total at the input current equal to 100 milliamperes plus 0.92 milliamperes, 100.92 milliamperes, which is equal to 100.9 input current equal to summation of the collector current and the current flowing through this one I1, and which is equal to 0.92 milliampere plus 100 milliamperes, 100.92 milliamperes. Now the input power is given by whatever this current into the whatever this voltage, which is equal to 10 into 100.92 milliamperes, or it is equal to 1009.2 milliwatts. Therefore, this is the input power and 480 milliwatt is the output power. Therefore, the efficiency in percentage is given by output power P out divided by input power P in into 100. 480 milliwatt divided by 1009.2 milliwatt into 100, which is equal to 47.5%. Therefore, that is the efficiency of this Zener voltage regulator. Now, let us see another problem of 2026 gate question that carries 1 mark. Consider the circuit, that is, this is a circuit, very simple circuit. In that one, the voltage source is given here, which is equal to 100 sine 2 pi into 50t. 50 is the frequency. This is the input voltage. This is the diode is the resistance equal to 10 ohm. And there's another DC source is there, that is equal to 50 volts. And the diode is ideal. Given Vs equal to 100 sine 2 pi into 50 into t, and the DC voltage DC equal to 50 volts, and the resistance equal to 10 ohms, and the average value of the current flowing through the diode. What is the average value of the current flowing through the diode? And that is to be expressed in amperes, round off to 2 decimal places. Therefore, that is a question in which here you can see that input voltage is calculated, given as this is the input voltage in which it is equal to 100. It is equal to 100 sine 2 pi into 50 into t into IDC, or here 0 to pi, pi to 2 pi. Therefore, this is the input voltage, and the voltage DC voltage that is equal to this one. That is, here 50 volt is the DC battery voltage applied here. This diode gets forward bias only when this voltage is more than this 50 volts. Then only the diode starts conducting. Now let us see the current flowing through the diode. Now continuing the same problem, 2026 gate question. And now as the circuit, this is the voltage that is applied to the circuit. In that one, the voltage here, that is when only when the voltage, the input voltage is more than 50 volt, the diode gets forward bias, and that's the diode starts conducting. That is why you have to see what is the instant at which this voltage is going above this 50 volt. For that one, we have to calculate what is this. I am putting it as alpha 1. This angle is alpha 1. Or sine alpha 1, you have to calculate. What is this one? From that one, alpha 1 can be calculated. Therefore, sine alpha 1 equal to that 50. Once that input voltage is reaching to that 50 value, sine alpha 1 or equal to 50, or we can say that alpha 1 equal to 1 by 2 or alpha 1 equal to 30 degree or pi by 6. Therefore, this one is alpha 1 equal to pi by 6, and that continues to conduct until this pi minus alpha 1, or that's equal to 5 pi by 6. For between this pi by 6 and 5 pi by 6, that diode continues to conduct. Therefore, the diode current can be calculated, which is equal to we have to see what is the resistance value. The resistance value equal to 10 ohms, and here we have to calculate what is the current. Of course, this voltage minus this voltage divided by 10, that is the current. Therefore, based on that equation, we can calculate what is the current equal to the input voltage equal to Vs minus 50 divided by 10. Therefore, Vs equal to, I am putting it as in terms of alpha here, 10 sine alpha minus equal to 5. Therefore, that is the current. This was 10 sine alpha minus 5 is the current waveform here. Of course, this is the current until this pi by 6, 0 current. From pi by 6 to 5 pi by 6, the current waveform or current equation equal to 10 sine alpha minus 5. From 5 pi by 6, again it equal to 0. The question is that we have to ask to find out what is the average value of this current. Therefore, now to find out the average value of this current that's flowing through the diode, you have to find out it is to be calculated, and of course the current is to be calculated, that is to be spread over 0 to 2 pi. That current is to be spread to almost, that is why it is equal to 1 by 2 pi, since the current is to be spread over this one time period. 1 by 2 pi integral pi by 6 to 5 pi by 6 integral I into, of course, d alpha, it is I am putting the alpha, d alpha, or 1 by pi by 6 to 5 pi by 6. Substituting that equation here, 10 sin alpha minus 5 into d alpha, again 1 by 2 pi into, it is equal to minus 10 cos alpha minus 5 alpha, and limit is again pi by 6 to 5 pi by 6. And if you substitute in that equation, in this equation, 1 by 2 pi into minus 10 root 3 plus 10 pi divided by 3, or here it is equal to, the answer is 1.08 amperes. The average value of this current is given by 1.08 amperes. Therefore, the average value of the current flowing through this diode, that is this one, only the diode conducts only between pi and 5 pi by 6, and we have seen the waveform of the current that is flowing through the, that is, this is a waveform, and we have calculated what is the average value of this current, which is equal to 1.08 amperes. Now let us see another problem of 2026 gate question, and that carry 2 marks. In the circuit shown, the open loop gain of the operation amplifier that is given as, that is equal to 105. And what is the voltage gain of the circuit? Round off to 2 decimal place. Therefore, the circuit is given here. It is a, of course, this is a inverting type of amplifier. Normally, we will be studying that the infinite open loop gain. But in this case, it is not infinite. It is specifically told the open loop gain is equal to 105. Therefore, based on that, we have to calculate what is the voltage gain. That is output voltage divided by input. That ratio is to be calculated. And in terms of, of course, the open loop gain equal to 105. Now coming to that one, again, I am writing the circuit as that the input voltage is equal to, let us see the circuit input voltage is given by, it is equal to 100 millivolt. 100 millivolt is the input voltage, and the resistance value, feedback resistance, equal to 100 kilo ohm, and the input resistance equal to 5 kilo ohms. And here the output voltage you have to calculate, and then can calculate what is the gain of the amplifier. And in that one, what is given is that the open loop gain is given as 105, and here the input impedance of this, that is equal to infinity, and the output impedance of the op amp equal to 0. These are the factors given. Now we have to calculate what is the ratio of the output voltage to the input voltage that gives the voltage gain. For that one, first we have to calculate. Of course, we have to apply the Kirchhoff's current law to this point. For that one, we have to first calculate what is the voltage at this point. What is the voltage at the inverting point? V minus what is the voltage. For that one, of course, the gain, we can say that one, the gain of the amplifier, the open loop gain equal to 105. Now, if you write the gain for that one, open loop gain equal to 105, and the input voltage equal to 100 millivolt, and R1 equal to 5 kilo ohm, and feedback resistance equal to 100 kilo ohm. The open loop gain, the definition of open loop gain is equal to output voltage divided by V plus minus V minus. Therefore, this is the definition of open loop gain. In that case, as I told you earlier, what we normally assume is that open loop gain equal to infinity. But in this problem, it is specifically told that it is not infinity, it is equal to some value, 105, it is given as the open loop gain. That is why here V0 divided by 0 minus, since the V plus equal to, because that's grounded, therefore V plus equal to 0 minus this voltage V minus, that's equal to, again V0 by V equal to, that means that V minus equal to this V minus, the voltage at this inverting terminal is given by, in terms of that one, which is equal to, we can say that one, it is equal to, if in terms of this one, it is equal to output voltage divided by the open loop gain. Therefore, V0 divided by, of course, here there's a minus sign is the, which is equal to the V minus equal to minus V0 divided by open loop gain. That is, we found out what is the voltage at this point. then we are going to apply the Kirchhoff's current law to this node as such. For the current coming towards this one, that is, we are applying the KCL to the inverting point here. The current coming towards is given by, it is equal to input voltage minus the voltage V minus, that is the inverting voltage, divided by R1. This is R1 I am taking. That's equal to, because we are assuming that it is given in the problem, input impedance or resistance equal to infinity. Therefore, the current flowing through this infinite, that equal to 0. For whatever the current coming here, that will be going through this feedback resistance. Therefore, here this current equal to this, since this current equal to 0, whatever the current coming here, that will be going through the output, or here V in minus V minus divided by R1, that is equal to V minus, that is this voltage, minus V0, that is equal to V0, V output voltage, divided by RF. Therefore, since the input current to the op amp equal to infinity, 0, because the input impedance equal to infinity, that is why we are writing this equation in this fashion. Now continuing the same problem, the open loop gain is given, the input resistance R1 is given, RF is given. Again, we have applied, as we have seen in the previous slide, we applied the Kirchhoff's current load to this node as such. Therefore, current coming this one is equal to same current flowing this one, because the input current equal to 0. Therefore, we have found out it is equal to the V in minus V minus divided by R1. That's equal to V minus minus V0 divided by RF, or that's also we have seen. And then we will be getting what is the, here, what is V minus? V minus already found out, which is equal to, it is equal to minus V0 by open loop gain. That is the previous slide. It's already we calculate, that is, you can see that one. We have seen that one, V minus equal to minus V0 divided by open loop gain. Already we calculated, and that is substituted in this equation. That is why it is equal to V in plus V0 divided by open loop gain divided by R1 equal to minus V0 divided by open loop gain minus V0 divided by RF. Then from this equation we can calculate what is the closed loop gain equal to, which is equal to V0 divided by V in. V0 divided by V in equal to closed loop gain in terms of this resistance. Or we can get, it is equal to, from this equation it can be derived that it is equal to minus RF by R1 divided by 1 plus 1 by open loop gain into 1 plus RF by R1. Therefore, this equation is the relation relating the closed loop gain of the op amp and the corresponding resistance value and the open loop gain. Normal case, as I already explained, now we will be assuming the open loop gain as infinity. In that case, this term will become 0. That is why normally we will be telling that the gain of a inverting amplifier equal to minus RF by R1. But in this problem, it is not infinity, it is given some value, 105 it is given. That is why we are deriving the equation for the gain of the op amp in terms of the open loop gain and the resistance values, input resistance R1 and RF. Therefore, that closed loop gain is given by output voltage divided by input voltage equal to minus RF divided by R1 divided by 1 plus 1 by open loop gain of the op amp, that is given as 105 into 1 plus RF by R1. Therefore, all the parameters are given, R1, RF, and whatever the already the open loop gain, everything is given. That is substituted in this equation, and then we will be getting it is equal to the gain, the closed loop gain V0 divided by V in, that is closed loop gain is equal to 16.66. Of course, this is an inverting amplifier, that is why it is equal to minus 16.66. Therefore, that is the equation, or that is the closed loop gain. Again, I am telling that only when if the AOL is equal to infinity, it is simply minus RF by R1. But in this problem, AOL value, that is open loop gain, is 105. That is why it is we have to derive the equation of the closed loop gain in terms of AOL, that is open loop gain, and these parameters R1 and RF. That is why this is the equation relation, and from that one we can calculate the closed loop gain is equal to minus 16.66.